Hello, my name is Kenia Verduzco. I am a fourth-year mechanical engineering major and the 2020-2021 Anteater Baja Racing Chief. The purpose of the Anteater Baja Racing project is to design, build, and test an off-road vehicle to compete at the annual Baja Race competition in 2022, and to provide our members with a meaningful learning experience that can be applied in real-world engineering positions. The team is organized into 5 sub-teams: front suspension and steering, rear suspension, brakes, powertrain, and chassis, body, and ergonomics. The Baja Race annual competition challenges 100 collegiate teams from all over the world to compete in a series of static and dynamic events. These events consider a range of aspects such as cost, design, efficiency, acceleration, endurance, and marketing. There are 5 dynamic events that we have to prepare for. First is the acceleration event, in which the acceleration of the car is measured by having a vehicle run through a straight dirt track of 150 feet. Next is the maneuverability test. For this, cones are placed to create a track with sharp turns that the cars have to be able to drive through. Third is the suspension test. This event includes several obstacles such as logs, bumps, poles, and a rock crawl as shown in the image to the right. Next is the hill climb or sled pull. These events are interchangeable depending on the location of the competition. For these events, they measure either the distance your vehicle is able to travel up a very steep hill or while pulling a sled that is gradually increasing in weight. Finally is the endurance race. This is a 4-hour-long race that combines all aspects of the previous events and measures the amount of laps that can be completed by the car within the time frame. Due to the harsh conditions of the race, cars constantly fail and have to be repaired by the team before they can go back on the track to complete more laps. In the past 2 years, Anteater Baja Racing has come up with 2 designs to complete these obstacles. Our 2019 to 2020 design, named Vandal 1, has a rear-wheel drive, an independent front and rear suspension, a steering linkage design, dual master cylinders, and a continuously variable transmission. The total weight of the car, including the driver, is 526 pounds, with a max speed of 30 miles per hour and a turning radius of 10 feet. This year, Vandal 1 was at the testing stage of the engineering design process. Second, we have Vandal 2, which is our chosen design for the 2022 competition. The main difference between Vandal 1 and Vandal 2 is that Vandal 2 will have an added 4-wheel drive feature, which is required for the next competition. The steering system also changed into a rack and pinion design, and the brakes will have a tandem master cylinder. The suspension and transmission aspects will remain the same. Vandal 2 will have a total weight of 585 pounds with a max speed of 27 miles per hour and a turning radius of 8 feet. This year, Vandal 2 was in the design idea and the manufacturing stages of the engineering design process. More about the progress made for both cars will be discussed in detail by our sub-team members.
Hi, I'm Taylor Ozuna, and I'm a 4th-year mechanical engineering major, and I'm also the chassis sub-team lead for the 2020-2021 school year. So our main focus of the quarter is the manufacture of the chassis, and the activities we did in order from left to right are profiling using angle grinders, tube bending, and welding. So for profiling, our team members would obtain a profile drawing for a specific tube in SolidWorks, and then we would use it as a template to cut a specific tube in its necessary shape for welding. Then onto tube bending. So we use a tube bender to bend the tubes as specified in the CAD model. And then we would actually draw out the bends to verify that the angles met the specifications in the model. Then finally on to welding. So our team chief, Kenya, and we both tack welded the chassis parts together using a MIG welder. The rest of the team will explain in detail what sections of the chassis we worked on and what was completed.
Hi, my name is Abigail Knapp.
And my name is Maya Dunlap. One of our main tasks this quarter was to manufacture the cockpit floor. The general dimensions of the cockpit floor includes a longitudinal underseat member at 26.5 inches and the base of the rear roll hoop at 25 inches wide. The cockpit floor is meant to protect the driver from the rough terrain of the track and provide a base for the seat. In addition, it provides a base for the rear roll hoop and the side impact members, which also aids in protecting the driver from potential impact.
We created the floor by bending primary tubes for the outside, then profiled secondary tubing to fit inside. We created a jig using a 1-to-1 ratio drawing of the entire floor and a large piece of plywood to hold the tubes in place. As seen in this photo, the tubing is placed on the jig to help with proper alignment. This helps ensure that all the profiles are flush and makes it easier to be tack welded.
Hi, my name is Ricky Smith, and I'll be talking about the rear floor of Vandal 2. The purpose of the rear floor is to mount the engine and the rear powertrain components. As shown on the left picture, the center distance between the back end of the rear floor to the rear roll hoop is 27.75 inches. This is the cab model of the Vandal 2 chassis, and the rear floor members are colored in green to indicate where on the car it belongs. Shown here is our actual chassis of Vandal 2, and towards the back you can see the rear floor members. In order to assemble the rear floor, we created a jig using a full-size skill drawing and wooden knobs. The drawing and knobs will allow us to correctly align the members together before welding. On the left, you can see how the jig was set up, and on the right, you can see the result of using the jig as the rear floor has been tack welded, looking exactly like the CAD model.
Hello, I'm Ryan Gruber, and I'm a fourth-year mechanical engineering major. The Baja race car is designed as an off-road vehicle for traversing rough and uneven terrain. Due to this complication, the chassis overheads were added to the frame to protect the driver in the event of a rollover. This causes the Baja chassis to be much taller than the conventional speedway race cars, since the overheads take up much more space. As you can see, the highlighted members in blue are the roll hoop overheads.
Hi, I'm Cameron Lee, and I'm also a fourth-year mechanical engineer. And so to manufacture these, we used a tube bender to get these 4 bends right here. And then after that, we used an angle grinder on the ends here to make the tubes fit around the chassis. This was so we could tack weld the ends together later on. And one thing that proved to be difficult was getting these 2 bends right here because they're in a different plane from these bends. And so we solved this by using an angle measuring instrument to get the right offset. And so next you can see, the comparison between Vandal 1 and Vandal 2's design. Vandal 1's roll cage, therefore roll hoop overheads are all 4.7 inches taller than Vandal 1's. And so that was something to accommodate the powertrain's 4-wheel drive. And then here's a picture of 2 of our members, including Ryan, angle grinding the ends of the overheads. And then here's the finished product that we had.
Hello, my name is Claudia Flores, and I am a second-year transfer mechanical engineering major, and I will also be the chassis, body, and ergonomics sub-team lead for the 2021-2022 school year. Our future plans include continuing the manufacturing process of the chassis. As you can see on the left, this is how the chassis stands right now, with just the powertrain floor, rear floor, and the rear roll hoop tack welded together. Once we bend and profile the other components, we will tack weld them to the chassis. Then we will hold a technical inspection to verify its rule compliance. Once that is done, we will fully weld all of the chassis components. For comparison, the picture on the right shows how the final chassis model should look like.
Hi, my name is Ryan Chung, and I am a third-year applied physics student, and I am the powertrain sub-team lead for Anteater Baja Racing. For Vandal 2, we finished designing the belts, pulleys, belt rollers, and shaft mounts for the new all-wheel drive system, ordered parts and materials for manufacturing, including a handbrake for the all-wheel drive's engagement mechanism, pulleys, and belts. Testing Vandal 1 consisted of a successful acceleration, temperature, and brakes testing done on the parking lot asphalt, redesigning and manufacturing CVT guard for testing on an off-road track, and establishing an off-road testing plan and CVT tuning procedure. Future plans include off-road testing for Vandal 1, manufacturing Vandal 2's mounts and shafts, and design of the belt guards based on ordered parts.
Hi, my name is David Lujan, and I'm a part of the powertrain sub-team and will be the powertrain team lead for the 2021-2022 Anteater Racing Team. My main goal this quarter was to help create the CVT guard by welding all of the metal pieces that were bent by our sub-team lead, as well as creating a guard and attaching it to the CVT. My secondary objectives were to help brakes team by testing the brakes and breaking in the new brake pads that we received, as well as doing acceleration testing, as shown here. As we can see in the video, all of the wheels lock except for the front right one, which we're still working on that, but all the other ones successfully fully lock when the brakes are fully extended. And here are some of the data that we received from the acceleration graph that we still have to pass through low pass filters to filter out the noise and find the acceleration of the car.
Hi, my name is Subin Khan, and I'm a member of Baja Racing's powertrain sub-team. This quarter, I was mainly in charge of four-wheel drive and manufacturing of Bendel 2, as well as manufacturing and testing of Bendel 1, specifically braking and acceleration testing. One of the things that I worked on for Bendel 2 is designing the front spool differential that will be transferring power from the belts to the front axles, which is still in progress. This is the guide roller that I designed. And for the FEA, I did stress and strain analysis. And as you can see, the results met the requirements. Another thing I was in charge of is choosing the appropriate V-belt and timing belt. In order to do so, I documented how to find the right belt for the engine power we have. Also, depending on the size of the belt that can handle the engine's horsepower efficiently, I chose the pulleys that can fit our vehicle as well.
Hi, my name is Andrew Gonzalez, and I'm a member of Baja's powertrain sub-team. One of my tasks for this quarter was to find a way to reduce the weight of our current gearbox. So these are the gears that we have. As you can see, they're pretty standard gears. Compared to our previous gears, I was able to reduce the weight by 1.25 pounds. After drilling holes in the gears, I performed some FAA to make sure that we would meet the same requirements. So as you can see from the results, we're pretty much in the safe zone. Given that I did simulate a worst case scenario where this gear would be spinning and this one would be static, we have a pretty high value here, but yet again, that's a worst case scenario. Another thing that I helped my team with this quarter was to improve our gearbox casing design. And we added oil leveler here, so we can essentially look inside and see how much oil we had. Lastly, we added a breather hole, as you can see here. So essentially, that's going to help the gearbox run at a much more.
My name is Nick Vera. I'm a member of the powertrain sub-team, and I worked on the design of the CVT guard as well as the all-wheel drive engagement mechanism. For the design of the CVT guard, I wanted to address some clearance issues that were present with the previous iteration. When the car was under intense load, such as acceleration, the CVT belt would bow outwards and come into contact with the flat walls on the previous design of the CVT guard. The new design addresses those issues by bowing outwards. So that way, under intense load, the belt does not come into contact with the walls of the CVT guard. The new design also allows for the tightening of the set screw, which was not possible with the previous design. For the all-wheel drive engagement mechanism, we're using a belt-driven all-wheel drive system. Basically, the driver of the car will use a handle connected to a pawl and ratchet style engagement mechanism that's connected via cable to the idler arm and idler pulley, which apply tension to the belt engaging the all-wheel drive system. And I'm working on improving the design of the idler arm and pulley.
Hi, my name is Evan Wu, and I'm a third-year mechanical engineering student, and I will be next year's brakes lead. In the brake sub-team, we are tasked with three main goals. One is to ensure that all of our wheels will lock when braking. Two is to properly maintain all of our brake circuits. And three, to ensure that our brakes assembly is following SAE Baja requirements. This quarter, we focused a lot on troubleshooting and testing Vandal 1, as well as redesigning some components for Vandal 2, such as the gas pedal and brake pedals, as access to manufacturing and acquiring these parts have become far more difficult due to the current pandemic.
Hello, my name is Brian Lee, and I'm currently a fourth-year mechanical engineering major and the current brakes team lead. So for the past year, one of the main goals of the brakes sub-team was to test the previous year's car, which was dubbed Vandal 1. And before we could even get to testing Vandal 1, we actually ran into a couple of issues with it. Namely that all four calipers on the car would not lock the wheel it was assigned to, as you can see in the short video. So as you can see here, the driver actuates the brakes, but none of the tires lock. And this was the crux of our problem for this past year. And so as a result, we actually had to troubleshoot some issues with the brakes. So figure 1 shows us bleeding the brake fluid, and we actually did a full brake fluid flush from the system, including the master cylinder. And figure 2, we re-greased the brake caliper post on all 4 calipers just to get them lubed up and able to move smoothly. And figure 3, we replaced the 2 front caliper pads here and here, these black ones, because they were quite run down. And due to these troubleshooting measures, we're actually successfully able to lock all 4 wheels because of this, as shown in this video. And there you go. Just super quick lock on the wheels. Even with slow-mo, it's really hard to tell.
Hi, my name is Eddie Huang, and I am a third-year mechanical engineering major, and I'm a part of the brake sub-team. With Vandal 1, we made a few adjustments on the braking system for Vandal 2. We switched from 4 milliliter brake reservoirs to 7 milliliter reservoirs due to the lack of availability of 4 millimeter reservoirs. We redesigned the gas and brake pedal phases to be half the thickness of those on Vandal 1 in order to cut down on weight and minimize the material needed to manufacture these parts, while still maintaining enough strength. We also made the pedals thicker to meet the thickness of the sheet that they'll be cut from, and we adjusted the size of the holes to account for the tolerance of the cutting process. Here you can see the results from the FEA on the new brake pedal. Applying 450 pounds of force, the maximum stress experienced is roughly 25,000 psi, which is below the yield strength of our material, 5052 H32 aluminum, which is roughly 28,000 psi. We plan to start assembling Vandal 2's brake system during the summer, around late June or early July, depending on when our parts arrive and when the chassis will be completed.
Hey, my name is Patrick Kelly, and I'm the lead of Baja's front suspension and steering sub-team. All right, so at a high level, our sub-team has a few responsibilities this past quarter. First of which is to verify the performance of the existing vehicle, Vandal 1, both in terms of suspension and steering performance. We also worked on building a simulation model of our suspension system for the team to continue to use and improve on in the future. We also continued to iterate the component design for our upcoming vehicle, Vandal 2, as well as begin the manufacturing of these parts. So a few details about this front suspension design for Vandal 2. We will have a ground clearance of 12 inches in the front and total wheel travel of 10 inches, split evenly between compression and rebound or droop. These values were chosen because of the foreseen obstacles and size of type of terrain that we expect in the competition environment. And for the frequency range the chassis or the vehicle will oscillate at, we've chosen 1.2 to 1.5 hertz. The exact value depends on the driver weight, but this range is firmly in the acceptable range for comfortable and supple type of ride for the bumpy terrain that we expect. On the steering side of things, we have moved from a linkage to a rack and pinion type of steering for this year's vehicle, mainly due to the increase in available steering angle lock that we will get from this, as well as the decreased driver effort. Our turning radius will still be within our requirement of under 10 feet. So I want to highlight this suspension model that we've been working on in a program called MSC Adams. This can be used and improved upon, but used to analyze the suspension geometry over travel, so the change in parameters like camber and toe over the full wheel travel, and also in a more dynamic sense and a kinematic sense, compare the performance and the handling of the vehicle to other designs before. So as I had mentioned, testing was one of the focuses of that our team had this quarter, and the drop tests of both the front and the rear of the vehicle independently was something we worked on. And this video here is a 36-inch drop of the front suspension independently. And on the right side, you can see plots of in both the time and frequency domain of an accelerometer that was mounted on the vehicle. The purpose of this test was to verify the performance of the suspension, specifically the frequency at which the chassis oscillates due to the shocks. So I'll play this video here. And from the frequency domain pictures on the right, you can see that our suspension is oscillating at the intended frequency.
Hi, my name is Kelly Ding. I'm a fourth-year mechanical engineer and a member of the front suspension and steering team.
Hi, I'm Julie, third-year ME major. In this quarter, I focused primarily on shock testing and steering mount manufacturing.
We worked on making the tie rod and clevis drawings so that they can be machined. Here you can see the drawings for the tie rods. Here you can see the drawings for the clevises. So another major task we worked on was manufacturing the steering rack mount. As you can see, we made wooden jigs in order to hold the individual square tubings in place so that they can later be welded together. We also printed profile drawings and taped them to each side of the square tubings in preparation for grinding.
And here are some pictures of Kelly and I profiling. As you can see, the sparks can get intense, so eye protection is crucial. And that's it for us.
Hi, my name is Joseph Parra, and I'm a graduating mechanical engineering student on the front suspension and steering sub-team. This quarter, we made a priority of planning and documenting accurate testing of Vandal 1, since we didn't have as much physical lab time due to COVID. In this video, we are performing a repeatable test to measure the steering radius of Vandal 1. As we push the car through a half-circle turn, the steering wheel is held locked at the maximum steering angle. We observe where the car crosses the tape measure line on the ground, and from that, we can calculate the steering radius.
I'm Andrew Eide, and I'm a graduating member of the Baja Front Suspension and Steering Sub-Team. The majority of what I did this quarter was testing and documentation for Vandal 1. One of the tests that we performed was tire deflection to help characterize the tires and assist in future simulations and calculations. We decided to do this test because in our analysis, we thought that the tire was able to compress and therefore act like a spring. The basic setup of the test is shown in the picture to the left, and what we did was inflate the tire to 5 psi and place a board on top of the tire and measure a distance from the ground to a marked point on the board. We then added a 50-pound sandbag and measured the new distance relative to the marked point as the tires compressed. We added sandbags and repeated the process up until there were 200 pounds resting on top of the plank. In our calculations over 3 trials, we found that the average spring constant was 85 pounds per inch.
My name is Mohammed Al-Farawi. I'm a mechanical engineer, and I will be the front suspension and steering lead for 2020. I primarily worked on control arm tube profiling, as you can see here, where I profiled the center arm to fit in between these two outer arms in the upper control arm.
Hi, my name is Matthew Ortiz, and I'm a 4th-year mechanical engineering student and rear suspension lead here at Anteater Baja SAE. Our goals for our subsystem include providing sufficient clearance for course obstacles during suspension travel, having the integrity to withstand worst-case loads, maximizing the grip on the road, and coordinating with front suspension to offer suitable driver comfort. To give a brief overview of our desired characteristics, we believe our goals will be met with a 3-link semi-trailing arm, 10 inches of total wheel travel with 7 inches of compression and 3 inches of drupal rebound, a rear ride frequency of 1.48 Hertz, and 50 inches of track width. Now, between the current car and the previous car, we switched to a box trailing arm to prioritize ease of manufacture, as well as increase the track width from 44 inches to reduce the weight transfer from one wheel to the other to improve grip during turns. I will now turn it over to my members to present their efforts in terms of manufacturing, generation of expected performance, design adjustments, and testing plans.
Hello, my name is Jamja Tashvar, and I'm a 3rd-year mechanical engineering student.
Hi, my name is Pranav Padinti. I'm a 3rd-year mechanical engineering major at UCI Irvine.
So this quarter, we wanted to focus on dynamic testing. So we wanted to find a way to simulate the situations we would go under in competition. So for the first example, so top left image, it would be a maneuverability test. So we would test a lot of the hard right turns and the steering of the vehicle. The second image, top right, we wanted to create an input frequency for the road. As you can see, the bumps have certain heights, and we wanted to simulate the response that the car would be under. And so for the bottom left image, we have the mud bog, and these are actual competition characteristics, competitions that the car would be under during the competition day. And in this image, you can see we graphed the display. We used MATLAB to graph the displacement versus force transmissibility, given a harmonic steady state response. So as shown in the previous image, we showed the bumps of the road having a certain frequency and having a certain height. So we simulated with different frequencies and different heights, and you can see as when the input frequency equals the natural frequency, there's both a maximum force that's transmitted to the chassis and a maximum displacement. So we really try to avoid that situation.
So we also worked on creating a new lower lateral link for our rear suspension. So the one we currently have is the one on the left, and as you can see, it's somewhat complicated with a lot of bends and therefore can result in high stresses in some points. So the one on the right is our simplified one. It fits in the exact same area as the original one, but it has far less bends and is far less complicated, therefore making it easier to manufacture and save material, which in turn saves weight.
Hi, I'm Dylan, and this quarter I focused on manufacturing the rear suspension components, including cutting and welding the parts of our trailing arm and lower lateral links, as well as helping to facilitate our laser cut orders. Additionally, I've assisted with the test plans and tests for Vandal 1, measuring the motion ratio and helping plan for track tests where we can verify our designs.
Hi, my name is Ricky and I'm a third year mechanical engineering major. I'll be talking about my design of the rear suspension limiting strap tabs that I've been working on this past quarter. In the blue highlight figures, you can see the CAD modeled upper and lower limiting strap tabs. The importance of the limiting straps is to prevent the shocks from overextension that could damage components in the suspension or drivetrain system. Because of this, getting the geometry involving the limiting strap stretching, shock travel, and ride height correct is crucial in getting the suspension as effective and efficient as it can be. I also conducted FEAs to verify that my design is capable of withstanding simulated worst case loadings with a high factor of safety that it may experience.